Okay. Hello, everyone. Uh, okay. For today's class, actually, I'm planning to at least 11.1 and maybe 11.2 sequence and series. Okay. I think last week we discussed the what is the sequence. Sequence is a list of numbers. It has order, and you will see a pattern in that sequence. Okay, and I think I gave you the example, and yeah, this should be. I think I write squared before. It should be n. Okay, and anyway, every time you see some list of numbers, and you can maybe make out a pattern from it, make a formula for how this pattern can be. Like for example, if you are dealing with from n 1 until some number, and you can try to plug in one by one and equal 1 and equal 2. And if you can find how the sequence can be formulated, then it is a sequence. But not all sequence can be formulated easily, or we can say that it doesn't have a simple definition. Okay. Let me write here just some examples. Okay. Some sequence that don't have a simple defining equation, but somehow we can write this sequence. Like for example, the populations. Okay, population. Population of the world. Let's say as January 1st in the year n. We can write maybe pm. And we don't have exactly what define this population, right? The digit number in E, okay, if you let an be the digit in the nth decimal place of the number E, then the sequence an is a sequence whose first terms, let's say the first terms is based on the decimals on E, okay? 7, 1, 8, 2, 8, 1, etc. This is just an example, and we don't really discuss much about this example. Not really a simple definition, but more discussion will be in the pattern. Okay, the pattern. And then I think the famous one that you know, I think it's called the Fibonacci sequence. Okay. Or let's say we write this as Fn. It's defined as recursive. Do you know recursive means? Let me write. If F1 is 1, F2 is 1, and let me write here. Fn is Fn minus 1 plus Fn minus 2. And n should be started from 3. And that's why you have 1, and then 1, and then 2, and then 3, etc., etc. Okay. Or maybe just let me just write. Okay. Okay. Okay, that's just a few examples for a sequence that doesn't really follow a simple pattern. Okay. And the important thing in sequence is how we approach the sequence, okay? How we visualize the sequence. Okay? So let me write here. This section is called limit of a sequence. So before we deal with the limit, let me write some notes. Okay. We can plot the sequence. Let's say we can plot like a graph with the axis is n and the y-axis is an, the sequence. So we can start maybe from 1, 2, 3, 4, up some number, and then the plot will be n and an. Okay. Let's start maybe from 1, 2, 3, 4, 5, 6, and 7. And for example, if we have an, let's just say we have n plus 1. Okay. An can be half, and then 2 over 3, 3 over 4, 4 over 5, and etc. Right? And if the an, to give you a good proportions, let me draw maybe 1 is here, okay, and give you different color. So maybe half is here. So this is 1 and half. And then 2 and 2 over 3 maybe here. And then 3 over 4 maybe around here. 4 over 5. And let me draw the line from this number 1. And eventually, you will see when you increase the number, when you increase the n, it will grow and approaching this one. And when you maybe review the calculus 1, you deal with the limit. It is same approach when you are approaching some number with limit. Okay, so let me write here. Continuously, it's getting closer. Let me write here. Getting closer to 1. Okay. And we can, beside these visuals, we can also make visualizations like we did last week when we did the visualize the Zeno paradox. We can also visualize from here. Let's say this is 1. Let's say this is half is our first terms, right? This is A1. And then maybe this is A2 and A3, A4, and then you will see it's getting closer to 1. And you will see the gap in between this sequence is getting closer, right? And to visualize how close that is, we can visualize this graph, okay? Okay. Okay, let me write the terms an equal n over n plus 1 approaching 1 as n becomes large. And the difference between the, let me change the color, between 1 and the sequence itself, the difference can be made as small as possible by taking a large n, right? So this definitions is uh, similar or uh, close by our limit understanding. Okay, so when we are uh, taking as much as we want, the n, the gap from the graph from here, from the red color there, it's getting a smaller, smaller, smaller. Okay, so we can write limit as n getting infinity. N over n plus 1 is 1. And the notations can be written in general and an, and we say we have some value there. So a sequence an has a limit L or we can also write or how to read the notation is as L approaching wait, wrong. As AN approaching L, AN approaching L as N approaching infinity. Okay. And we say the sequence converge or convergent if you want, if limit exists. And then sequence diverges, limit doesn't exist. But I think it's not too complicated. It's easy to understand. So when you have a sequence, any sequence that you find the formula and you check the sequence, and if the sequence from the number, you can see that maybe it will be converges into some set of number when you increase the n, and you say it's convergent. But if you cannot conclude, probably it will be divergence. We will deal with all those methods later in more sections. Okay? And in limit, we also have the precise definitions of limit. So let me, or any questions first before I move to the next section? Okay. Okay, let me move to the next section. It's precise definitions of limit. Basically similar with our calculus 1. Of sequence. Okay. I will write sequence just SEQ to make it simple. So sequence, let me write sequence AN has limit L. So we write limit, let me write in blue. So limit and approaching infinity, AN equal L, as L and the different form from the regular sequence or the regular limit is we need to get in more detail of the small gap. Okay. So if for every epsilon there will be corresponding integer n such that if the small n is bigger than this n, okay, then the difference between the an and its value is less than epsilon. Okay, so first, I hope you still remember the epsilon things. So epsilon means because if we talk about the limit, when we talk about the Zeno paradox, when we are trying to reach the wall, but we only can move like every half set from previous moves, actually, in a real life, if we are trying to simulate the situations, we are never going into the wall, right? Like maybe if the wall is like 1 meter, we can go maybe 0.9999999. And how about the 0.00001? Probably the smallest thing that you can think. That's the condition. So precise definition of limit, like in calculus 1, is trying to define the smallest thing that we can think, and that is the epsilon. Okay, the epsilon. Okay, and if we trying to illustrate the in line, okay, the sequence. Let's say it's from 0. Let's say it's A1, A2, A3, or maybe let me write in a random so that it will be more natural. Maybe A2 is here. Wait. And A3 is here. So it's moving forward, backward. Oh, wait a moment. Let me check. Okay. And then maybe A4 is here. A5, A6, and so on. Maybe middle. Like for example, let me illustrate the L. Let's say this is the L. So it should be, what I want to show you is from 0, A1, A2, it will be moving randomly, but eventually when n is getting bigger, it will reaching the L, like we did before. But this is in more random sequence, so that you know that it's not always like you have 0 and then A1, A2, and then getting closer, 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 closer. That's a simple sequence. But in a real situation, when you find something that you want to formulate it, sometimes when you simulate the data, you will find the random set at the first time. But maybe the data set can converge into a specific solution or specific numbers. So maybe from A1, A2, A3, and then it's getting here, but it's getting closer here. And eventually, okay, it's around this L. Okay, and what I want to write here is I just want to show you the subset of the L. Let's say this area here. Let's move L around here. And let's say this is L minus epsilon, and this is L minus epsilon. So imagine actually this gap is really small. Okay, really small. So epsilon is really small. Okay. And maybe around this L, this is the some sequences defined by the number of the integers. Okay. Okay. Maybe it's not really good if you see from here. Maybe we need to take another graph to define this L. We can do the same thing as previous regular limit definitions, you can take a graph. Let's say this is L, and let's take line around here. From 0, maybe 1, 2, 3, 4, 5. This is N, this is IN. Or maybe make it longer. And this is the number, the N integer. And let me use different color. And let's say we have the L plus epsilon and L minus epsilon. Okay. So the gap here is the epsilon. Okay, the gap is epsilon. And maybe we can plot the point, and maybe it will going here. And of course, if we are seeing this graph, we say it's converged. Okay, we say it's converged. Maybe I'm giving you the another example. For example, if you have graph like that. Wait a minute. Like for example, it's going up, and then we are not sure when will the N will stop. We conclude this also diverge. If, for example, you have this, if it is not concluding into a value, and it's also diverge. Okay, it's also diverge. And in infinite limit, precise So limit as n approaching infinity equal means for every positive, let's say big M like that, there will be integer n such that if n uh, and similarly if limit and you also have the limit laws, but I think limit law is basically the same as the calculus one, so I don't need to review. Okay. Um, limit laws, maybe power law. So if you have limit and approaching infinity, and with the power of p. Okay, so it means limit p. So if p greater 0 and an greater 0. Also, you have the squeeze theorem. Okay, so basically it's reviewing some part of limit. Okay, I hope you still remember. Okay, and the squeeze theorem. The squeeze theorem. And basically it's the same, but we change the functions into sequence. Okay, we change the function into sequence. Usually we are dealing with functions f. Maybe this is the situations, but in the sequence we just changing all the function into sequence. For example, an and bn and cn. All this is sequence. Okay, sequence. So for n is greater than n 0, limit n approaching infinity of an is the same as limit as cn is equal L, and then the limit as n approaching infinity, Pn is also L. Okay, but this is happening if you are already proving that Bn is in between An and Cn. Okay, if you can prove that Bn is in the middle, then you can apply the squeeze theorem. If you know limit An and limit Cn is L, then you can prove the Bn is also L. It's same thing and in calculus 1. Okay, same thing. You just change the a and b and c and okay. In calculus 1 is the functions, right? And we change into the sequence, and we treat the sequence as our functions actually. Okay. For example, if uh, if you want to visualize what is happening, maybe okay, for example, like that, the plot. Okay, this the squeeze, okay, squeeze theorem, and then another theorem is if limit n approaching infinity, if this is 0, then is also 0. Okay, the absolute value. This is useful if you find sequences that have negative terms. Okay. Um, okay, we'll give you some examples. So find example. Find limit n approaching infinity and n plus 1. So basically, you need some review on limit. If you feel you need to review limit. Okay. So if you remember a limit, basically this just treat the sequence like functions. So so limit up, we can write and change the form and divide all by n. And by doing so, we can get 1 over n by our definitions in limit if we can conclude this 0. So it's actually 1. Okay. And this actually, the sequence is what we are doing in the first, in the intro. So by using limit, we can just conclude it's 1. Okay. Okay. I hope you get the relations. Okay, between the how we approach the sequence and the limit. Okay. Let me check. Okay. Now the next one is AN converge or diverge. We can deal with limit, right? Just use this. And let me just divide all by n. So the top one will be just 1. And the bottom one will be, because it has square root, it will be then squared. And then this will be 1 over n. Okay. What will happen? It's getting 0 here, right? And it's getting undefined. Okay. Or if you want, you can just write the infinite symbols. And it's divergence or diverge. AN diverge. And then what will happen if AN is let's say converge or diverge. Same thing with using limit. We approach the sequence and we are now in situation where it's both infinite, right? Both infinite, and we call this indeterminate forms. The way we solve indeterminate forms, one way is using the L'Hopital rule. You just need to derive the top one and derive the bottom one. Okay. And do L'Hopital here, and limit. It will be 0. And what if the sequence is converge, diverge? Now we can write this as the sequence is, let's say, from n is 1, it's -1, and then squared, and the cube. We have this sequence. And if you see, we cannot conclude anything, right? It's -1, +1, -1, +1, and that means it's diverge. Okay, it's diverge. Okay, I think you can see some examples from your textbook, but I think I'm just skipping that and focus on so if you have sequence is R with the power of n. It's if it is convergent if and divergent for all other values R. And other parts will be a diverge. Okay. Okay. Another part in sequence is we call monotonic and bounded sequence. So monotone means it moves maybe increasing, always increasing, or always decreasing. Okay, and it will be bounded on some value. Let me write the definitions. Sequence AN is increasing if AN plus AN plus 1 for all n greater or equal 1, so that A1 less than A2, less than A3, etc. And sequence AN is decreasing if AN is greater than AN plus 1 for all n greater than or equal 1. So A1 greater than A2 greater than A3, etc. And monotonic can be increasing, can be decreasing. Or it's or. Okay, or. Mono, wait, monotonic. So by these definitions, we can figure how the sequence is increasing or decreasing. Okay. So for example, if you have an 3 over n plus 5. So if we check the, let's say, a n plus 1, this will be 3n plus 6, right? Okay. And since 3n plus 5 will be greater than 3n plus 6, then we can say the sequence decreasing. Okay. So if you have a sequence, you want to know the increasing or decreasing, what you need to do is you need to find n plus 1. So you need to just change n with n plus 1. Okay. So, okay. Another definition, sequence an bounded above if there is a number, let's say m, such that an less equal m or n greater equal 1. And sequence bounded below if there is a number, let's say small m, such that m is less than an. And if a sequence is bounded above and below, then it's called the bounded sequence. Okay, for instance, example, an equal n plus 1. It's bounded because it has 0, and 1 for all n, right? And an equal n is also bounded, but it's bounded below. Okay. Well, the other one is above and this is below, because an is greater than 0. So it will be bounded on 0 level. Okay. But notes, not every bounded sequence converge. Okay. For example, the an -1 n, it's bounded in every, let's say, in this 2 point here, it's bounded here, right? Up and down, but it's not converged. Okay? So not every bounded sequence is converged. And not every monotonic sequence is converged also. Okay, so bounded means it has a specific, let's say, stop point. Okay, and monotonic means it can always increasing, or decreasing. That's called monotonic. Okay, so increasing or decreasing is called monotonic. But you will know sometimes in a sequence, you cannot have like uh, always decreasing, always increasing. Maybe you need to define based on from which end. Maybe you will see, oh, it will be decreasing, but later it will be increasing. It's also can be conditions. Okay. Later I will maybe show you. But from here, we will have monotonic sequence theorem. Let me write here. So to make sure that it's convergence, first it should be bounded. So every bounded and monotonic sequence is convergent. This way we can define. If we just say bounded, then it can be, and it will forever like this. So it will be not converging into one point, right? So we need to say it should be bounded and monotonic, and it must be converged. Okay. So for example, okay, it's always maybe increasing like this. And then it's increasing, but at some point it will, like, it's having like a stop point. It's going steady like this one, and we say this way is converged, right? It's converged at this point. Okay, it's converged here. Okay, it's converged. So what should the theory say? It's increasing. It's always increasing, but it's actually bounded. And this way we conclude this is converged. Okay. If it just maybe only bounded but not monotonic, then you cannot conclude that. It will be probably diverge. If it's only monotonic, maybe it can be like this, always increasing, and it's not bounded, right? So it's also diverge. So to have converged, you need to have bounded and monotonic. Okay, both of them. Okay, I'm giving you maybe some exercise. So determine if it is converge, diverge. The first one, an equal 3 plus 5 and square. Okay, giving you maybe several minutes to try and solve it. I think most of the questions here is reviewing the calculus 1 limit, right? And yeah, basically we are uh, doing the calculus limit here. I think like the first one here, 3 plus 5n squared n plus n squared. You can see from the terms here, it has n squared, bottom has n squared, probably converge, right? Right. You can see from the pattern here. You can always see what kind of limit it is. Probably it will converge. And the other one like this and this, you need to do some algebra, simplify, and then use some limit law. And I think you can also find E also similar. When you have E with the power of -1 over square root of n, if you want to limit all of this, the E with this power, when you put limit here, it's actually the same thing as, because we only evaluate the n above here, then we can move the limit here, right? So E with the power of limit, blah, blah, blah here. And if we plug in infinite to up here, E will be 1, right? Okay, got it? And this 2 here, you need to do some algebra and try to simplify, and then basically doing the same thing as the first one. Okay. I believe the first one is easy enough. Okay. Uh, let me give you the ln. So let me write the ln. Ln. This having n plus 1 and then minus ln n. Okay. This means ln of n. Okay. Meaning we can write ln n plus 1 and then over n. Okay. And next thing, we can move the limit. Okay. And we can evaluate the limit inside. Okay. Eventually, you will get you can divide by n, 1, 1, and 1 over n. So 1 over n is 0, so 1, 1. So it's ln 1. Okay. So we can say this converge. And this E here, we can limit. Let me write the complete form is -1. And then we can move the limit above. And eventually you will realize that, okay, it's actually 1. Now how about the last one here? Cosine squared n and 2 with the power of n. Is it converge or diverge? And how you find? Mhm. Yeah, how you get this? Any idea for the cosine squared n? One minus. Hmm. But the, yeah. That's the problem. Anyway, I think I don't know why, because the weather like yesterday is quite cold, and then I think since the morning and afternoon it's changed to really hot. I think that is the reason why this class is so sleepy. Honestly, I also a little bit sleepy. I don't know why. I think that's why. That's why, because this sudden transition between the temperature. Yeah, I think that way. Like when you are exercising in the cold temperature and exercising in the hot temperature, it will be a little bit different. Okay. Because the when temperature changes, the pressure changes, right? The pressure in your body changes. That's why you feel sleepy, and that's normal. I don't mind if you sleep in my class. I don't mind. Because we cannot really forcing uh, like, okay, we are trying to awake, blah blah blah, but it's nature, right? Human natures like to sleep. I don't mind. Okay, uh, back to here, and after we finish this cosine, I will go to 11.2, maybe a little bit, and we will have like early finish. Okay, we will finish early. This way, remember that we still have the squeeze theorem. Okay, we still have the squeeze theorem, and we can use the squeeze theorem to solve. So first, to use the squeeze theorem, we need to define, or we need to prove. Let's say I will give you the exact answer is this. Okay? But actually, we need to use to prove uh, that this is true. Yeah, we need just to prove this is true, and then we can use the limit as n approaching infinite of this sequence is 0. That means if we are doing the cosine squared n over 2 with power of n is also the same. Okay. So we can say that the sequence of AN is converged by Squeeze theorem. Okay. I think before we go into 11.2, maybe I'm giving you example for the monotonic sequence. I forgot to give you example. Example of monotonic. So the questions, does the AN equal 3 over n factorial Okay, this is interesting. Okay, the question is just asking. You have the formula here, 3 with the power of n over n factorial. Is this converged or what? Okay, how to know converged or not? First, we can plot. Okay, try 1, try 2, try 3, maybe until 4 or 5, and you can see what will happen. Okay, let's just write from 1. So from n equal 1, a1 is 3 over 1, so 3, right? And equal to a2 is 9. 2 factorial is just 2. So maybe I can write 4.5. And n equal 3. Let's just say it's 27 divided by 6. This is actually same thing, right? And n equal 4. 81, right? 4, 3, 12 to 24. Divided by 3 will be 27. 8. Okay. Maybe one more. 5. Okay. 3, 5. Let's say it's 3, 60, right? 5 factorial is 20, 60, it's 120, right? So it will be, okay. Okay, what is happening here? So this is also the same 4.5. This is around 3.3 something, right? and this will be around 2 point something 0 something number. Okay. So what's happening here? You will see that from 1 until 3 here, we can say that it's mostly increasing. So increasing and then stop same number here. And then from here to 4 and to 5, it's going down. So we can see from all the case here, okay, from 1 to 2, it's increasing. But later, from 3 until maybe, but if you check, it will always decreasing. It will always decreasing from 3. Okay. So from for let's say 4 and greater than 3, we know that 3 over n is less than 1. So from here until here, it's converged. If you check the number, it will be monotonic and bounded. Because it's monotonic and bounded, it will be converged. Okay. Oh wait, why is minus? Let me write in the next page in more details. If you check maybe A10 maybe, or maybe A20, let me write down for you. This will be around, or you can check by your calculator. Okay. Meaning it's 0.000 something, right? And intuitively we will say, okay, it will reach 0. Okay. We can actually solve this by using our definitions. Okay. And should be start from 3. And from here, we can at least having this expression and giving the equations. And now we can try to simplify. We can cancel this, and it will be 3, right? And we can cancel this, and it will be n factorial, right? So n factorial. Wait. Wrong canceling. Sorry. This and this. Okay. So n plus 1 over 3. Okay, correct, right? So n plus 1 should be greater or equal 3. So n at least should be from 2. So we can solve this that it will be decreasing from n greater or equal to. Wait, not be good here. Be here. Okay, that's one example how you use the uh, theorem in monotonic bounded sequence. Okay. Okay. Any questions from here? Okay. As long as the definition is correct. Okay. Uh, the other problem that you need to think of is just the algebra and the calculus one. Okay. Other thing is just a new definition in sequence. Okay. But still, how to calculate all of that things, it's based on calculus one. Okay. If we move to the series, okay, 11.2. What's the difference uh, the series and sequence? While the sequence is only set of order, so sequence is set of order. And series is sum, okay? Sum of the order. For example, like the Zeno paradoxes, if we plus all the half plus this is also series if we enlarge the n until infinite number. And if you are see the pi as a number, if we write down the pi we can divide. Okay, divide this pi becomes 3 plus and plus and plus dot dot dot. So behind this pi is actually we can divide become this all this number, and if we add more and more terms, we increase the n. The result will be our original pi. Okay, original pi. So if we try to add the terms of an infinite sequence, we get our I will write directly. It's A1 plus A2 plus A3 plus dot, 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 plus AN plus dot, dot, dot. We call this infinite series. Or you can just call the series is also fine. And it's denoted by or the complete one. But usually if you just write sigma and it means, okay, it is a sequence, but you need to plus the sequence, so that is the series. Okay. Okay. Okay, maybe just giving the definitions and then we can finish the class. So definition, given series and AN is A1 A plus A2 plus A3 plus, okay, and let the Sn denote its partial sum where the Sn, or let me change the color, Sn is the sigma of n equal 1 AI equal A1 plus A2 plus A3 plus dot, dot, dot. Okay. And if the sequence is convergent, and limit let's say it's equal as is exists as a real number, then series AN converge or convergent. And we write or equal as. And as means, or it's called the sum of the series. If a sequence is divergent, then series is divergent. Okay. But I will explain more in Thursday class. Okay. Okay, I think we finished the class until here. Okay, and we will see you again on Thursday.